All right, guys, the last section that we are going to look at in this particular module is section 4.8, and I know that word looks weird. It looks like El Hospital or El Hospital. It's actually Le Hopital's rule. So we are going to look at this. I had debated on whether to show you this or not. Some instructors skip this section. One of the reasons I want to show you this is just in case you plan on going to Calc 2. So I'm not going to do too much with it. I just want to glance at it for a moment. So the first thing I want to look at here is what it actually is. So in this section, we examine a powerful tool for eliminating or evaluating limits. This tool, known as L'Hopital's rule, uses derivatives to calculate limits. So with this rule, we'll be able to evaluate many limits we would have not been able to determine. So instead of relying on numerical evidence to conjecture what a limit exists, we'll be able to show definitively that a limit exists and to determine its exact value. So in previous sections, when we got these indeterminate forms, we were just kind of stuck. We couldn't figure out, algebraically how to come up with that. So this is what L'Hopital's rule does. It actually allows us to figure out for some of these indeterminate forms. So to apply, and here's this idea of indeterminate forms. So one of the indeterminate forms we looked at was 0 over 0. We've looked at infinity over infinity or negative infinity over infinity. There's a couple other ones that we're going to talk about mixed in here. So you guys can read all this. Here's our 0 over 0 case. So basically what this says is if the limit as x approaches a of f of x equals 0, and the limit as a approaches g of x equals 0. In other words, and so we're going all the way back to what we first started with calculus here, is this idea of limits. If you're trying to take the limit of something and you try to do that direct substitution, and you get 0 over 0, and you can't simplify it anyway, this is a way you can work around that. You can actually take the derivative of the top and the bottom, and you can keep taking the derivative until you get it to a format that is actually good for you. And it's gonna, so assuming the limit on the right exists or is negative infinity or positive infinity, this result also holds if we're considering one-sided limits. So you just keep taking the derivative of the top and the bottom until you get a form that actually is going to provide you an algebraic answer through direct substitution. And we keep going here. Here is the infinity over infinity case. It actually turns out it's the same thing. You just take the derivative of the top and the bottom, and you keep doing that until you get something that you can take the limit of through direct substitution. There are other indeterminate forms. I'm trying to make sure we get the... Now, here's the thing. L'Hopital's does not always work. So even though sometimes you can get this to simplify down to something where you can do a direct substitution, there is no guarantee that it will always work. So just be aware of that. We do have other indeterminate forms that we can use L'Hopital's for. These include 0 times infinity, infinity minus infinity, 1 to the infinitieth power, infinity to the 0, and 0 to the 0 power are all considered indeterminate forms. These expressions are not real numbers. Rather, they represent forms that arise when trying to evaluate certain limits. Next, we realize why these are indeterminate forms and then understand how to use L'Hopital's rules in these cases. Guys, I'm not going to do a terrible lot with these. These are weird forms that just randomly show up. Like it may be sections down the road. You may be in Calc 2 and one of these weird forms shows up and you're like, well, how do I take the limit of this? I don't know how. And this is one of the ways that you can go about doing that. Trying to see if there's anything else really important. I don't care about the growth functions here. That's an algebra idea. All right, so all I'm going to do is a couple of examples of this so you can look at it. So like on 357, evaluate the limit. And they do tell us the limit as x approaches infinity of e to the x over x to the k. So a lot of times the way that you use L'Hopital's rule is you talk about what happens in terms of, as you head towards infinity in this case. So if you think about e to the x, e to the x, starts off pretty low and then it really just takes off, right? This x to the k is a polynomial function. Polynomial functions just in general are not going to increase at the rate that a natural log is going to increase. So here's what happens really with this one. I'm looking at the end behavior that e to the x happens to be. Now I can try to apply L'Hopital's rule to this. If I do that, meaning I'm going to take the derivative of the top and the bottom. So if I use L'Hopital's, I get the limit as x approaches infinity. Derivative of e to the x is e to the x. The derivative of x to the k is going to be k x k minus 1. So this one's going to keep going farther and farther, or it's going to keep getting smaller and smaller and smaller and smaller. Now with this one, I don't want to keep taking the derivative because I'm never going to see this k x to the k minus 1 fall out to be just a constant, just because of the way it's particularly set up. So instead, I'm going to kind of think about e to the x is increasing towards infinity. I'm not exactly sure what k x to the k minus 1 is doing, but I do realize e to the x is going to overtake it. So whatever e to the x is, when you plug infinity in, that's what your answer is gonna be. So this is kind of a weird one. So if you look at what e to the x does, as e to the x approaches infinity, your y value is also approaching infinity. Now, again, like I said, this one, the algebra doesn't really fall out that nicely. If you're ever concerned about what these things are doing, graph them. Graph them and see what they're doing. Let's do another one. So I'm going to look at number 359. Now, on this one, the algebra is going to work out really nicely. So in 359, we're asked to evaluate the limit as x approaches a of x minus a over x squared minus a squared, as long as a is not equal to 0. Of course, a being equal to 0 is bad in this particular instance. So in 359, if I was to do a direct substitution, I'd have a minus a, which is 0, and a squared minus a squared, which is also 0. So that's why it's in the indeterminate form. But using L'Hopital's, I'm going to take the derivative of the top and the bottom. Remember, a is just a constant. It's just a number. So the derivative of x minus a is going to be 1 over, and I needed to put my limit. I forgot to put my limit. I don't really need my. Okay, here we go. So the derivative of x minus a is 1 over the derivative of x squared minus a squared is going to be 2x. And then the minus a squared, that's just a number that goes to 0. So because I've used L'Hopital's and I've taken the derivative of the top and the bottom, I can actually do direct substitution now. So if I plug my a in for x, I get 1 over 2a. And that's actually what the limit is equal to. So sometimes taking the limit works, sometimes it does not. And that's what the book was talking about. L'Hopital's does not always work. But that's pretty nice, right? You go from something it's an indeterminate form to something where you know what the limit's going to be. Now, I can't graph this one. This one just, there's too many unknowns to be able to graph it. But there we go. Let's do another one. We are going to look at, let's do 261. 261 looks not nice. We'll see what happens with it. Again, if I was to plug a in, I would have a minus a, which is 0. I'd have a to the n minus a to the n, which is also 0. That's an indeterminate form. So I'm going to try L'Hopital's, which says let's take the limit of the top and the derivative of the top and the bottom. So the derivative of the top, remember a is just a number, so derivative of x is 1. Ooh, which is, I love seeing these ones fall out. That means that I'm probably right there at the answer. And then if I take the derivative of x to the n minus a to the n, the derivative of the x to the n is going to be, bring down my exponent n, x raised to the n minus 1. I cannot take I can't take the derivative of a to the n, it's just 0. So this, whatever, when I plug my a in, that's going to be what I'm going to be approaching as limit as x approaches a. So this is going to be 1 over n. My x becomes an a to the n minus 1. And that is the limit of this thing. So if we knew what a was, if they give us a numerical value for a, that would be the answer that we got with direct substitution. So L'Hopital's is pretty cool. Again, you may or may not ever see it in my class because we don't really come across indeterminate forms that frequently. But in Calc 2, again, if you decide to take that class, it may randomly be that you get this situation where you can't take the derivative, or you can't take the limit, and this is a way to fix that. Okay, moving right along. I may just do all of these videos in one because they're not really that cool after some of the problems that you've done in this chapter. Let's look at, let's do 363. So on 363, they say determine whether you can apply L'Hopital's rule directly, explain why or why not, then indicate if there's some way you can alter the limit so you can apply it. So on 363, we've got the limit as x approaches infinity of x raised to the 1 over x. Now, we can apply L'Hopital's rule to this one directly. Now, if you notice with L'Hopital's rule, it was you had a function over a function, right? This is not the case. We do not have a function over a function. I have a function raised to a function. This is a composition. So L'Hopital's rule is not good for compositions. So with this particular one on 363, we could not use L'Hopital's rule because of the composition. If I went through and I took the log, so maybe I took the log and brought the 1 over x down, I could rearrange it to where I could use L'Hopital's rule. But for right now, I'm kind of stuck. Let's do 367. We'll look at that one. So 367, for the following exercises, evaluate the limits with either L'Hopital's rule or previously learned method. So in 367, the question is, do I need to use L'Hopital's rule? So we actually have done this problem back in chapter 2 and then probably 3. I don't have to use L'Hopital's rule. And the reason I don't is because if you'll notice, x squared minus 9, even though if I try to plug 3 in, I go to an indeterminate form, but x squared minus 9 actually factors out to be x plus 3x minus 3 over x minus 3. So this thing has a hole. We've already talked about ways to work around holes. So I cancel that out. So really, it's just the limit as x approaches 3 of x plus 3, which is 6. So please be aware that sometimes you do have to use it, sometimes you don't. Sometimes you can use the math that you've already come up with. Let's look at 371. So 371, we've got a trig function here. We've got the limit as x approaches pi of x minus pi over sine of x. There's no way to clean this thing up algebraically like I did with the previous problem. So I'm going to go ahead and use L'Hopital's rule. So if I use L'Hopital's, I'm going to have the limit as x approaches pi. So pi is the number here. If I take the derivative of the top, I'm going to get a 1. I love seeing 1s fall out of these because that means I'm on the right track with L'Hopital's. Derivative of sine is cosine of x. So if I do my direct substitution here and plug pi in, I'm going to have 1 over the cosine of pi, which is -1. So my final answer here is -1. Pretty nice. Let's do. So guys, this is just something in your tool belt of calculus to use to simplify things. Let's do number 377. So 377, I can already tell there's no way to clean this up with the algebra that I know. So I'm going to go ahead, jump in here and do L'Hopital's. My box will move out of the way to where I can write. So on 377, we're going to have the limit as x approaches 0 of, if I take the derivative of the top, I get e to the x minus 1 over derivative of x squared is going to be 2x. So again, this didn't fall out as pretty as I would have wanted it to. But guess what? Let's just take the derivative again. So I'm going to have the limit as x approaches 0 of derivative of e to the x minus 1 is just e to the x, derivative of 2x is 2. I feel like at this point, because I've got this number that is falling out on the bottom, I can go ahead and take the limit now through direct substitution because I don't have to worry about an indeterminate form. So if I plug 0 in, e to the 0 is 1, and the 2 doesn't change. So the answer to this one is 1/2. Let's do one more, and I think we'll call it quits on this video. We're going to look at number 381. Let's not do that. Let's just make it easy on ourselves. So 381, we've got the limit as x approaches 1 of the square root of x minus the cube root of x over x minus 1. Please note with this one, yeah, I can't clean this up any way that I would normally with using algebra. So I'm going to use L'Hopital's. So we've got the limit as x approaches 1. Let me rewrite this. This is x to the 1/2 minus x to the 1/3 over x minus 1. My hope is that I'm going to get one of these variables to go to a number. That's my hope. So if I take the derivative of x to the 1/2, I'm going to have 1/2 x to the negative 1/2 minus 1/3 x to the negative 2/3. Right, so 1/3 minus, yeah, over x minus 1. Nope. Derivative of x minus 1. Derivative of x minus 1 is just 1. So all I'm doing here is I'm concerned with what's on top. Not a lot going here on top because everything's just in terms of 1. So really I've got 1/2 times x to the negative 1/2, which, or x raised to the negative 1/2, which is just 1. So if I do a direct substitution, I'm going to have 1/2 times 1 minus 1/3 times, well, 1, because 1 to the negative 2/3 is still 1. So what's 1/2 minus 1/3? That's going to end up being 1/6. All right, guys, hopefully these videos help. So if you've got any questions, of course, I've got my office hours on Wednesday. Come hang out with me. I will see you later.